So we were really talking about the issues, what a cantilever can do. In general, scanning force, that means, as you remember, I have the gadgets brought back here, if you want to play again. So that means we have this cantilever either in contact or in non-contact by vibration. We go into it, and we saw during yesterday's also talks, everything goes back to this famous phase. You want to really learn something about the phase, and we believe that this is optics, okay, near-field optics. So there are many, many effects, and that's exactly what I would like to cover in this lecture, so to say, going really from scanning force methods in contact, in non-contact, and show you that everything we deduce from this phase can be many, many-fold, which means the bad news, we can make many mistakes, okay? The good news is there are ways how to differentiate between these different contributions, and that's one thing at different length scales, different interactions, putting up modulations, putting up sidebands, and other modulation techniques, and that's exactly the point. So this is actually the plan. I would like to start with advanced modes in contact, because imagine me going in a tapping mode, the tip goes into contact, and something must happen when your tip touches your surface. For instance, electrons might exchange, or in other words, you're changing the local electrostatic interactions, which means your balance forces go this way or that way, depending actually on what is going on. So we need to talk about what is there. I would like to really start with topographic resolution, lateral forces, so-called piezo response, and conductive AFM, because everything can happen at the same time when you tap with your tip on your surface. Then we will really proceed to non-contact and tapping. That means we go to the other side, which is the attractive or more attractive part. And that's actually the regime where we really can then deduce whether this is a true atomic resolution. One of the most hindering points also in SNOM is this guy here, electrostatics. And I would like to really spend at least 5 to 7 minutes on that, because you need to know how to compensate. And if you have a nice company like NearSpec, they're willing to adapt for these modes in a way that it's working. Yeah. So, and in the end, if there's time, please, Mrs. Chairman, you stop me if you can go for time resolved. And if I'm saying time resolved, I'm not meaning basically milliseconds or so, but we're talking here about picoseconds. So your machine, although very slow, piezo or electrically driven, can do really high resolution information on the picosecond length scale. Before I go I would like to advertise a conference we're organizing later this year, the last week of September in Dresden. It's called the DuProso Dynamic Properties. So we're not looking at the static ones, but everything that is dynamic on it, including SNOM. And if you are on your way back, basically from the Warsaw EMRS conference, just stop by Dresden, because we scheduled that exactly the week after the EMRS, actually in Warsaw. I will pop up that again. Otherwise, you can just type in DuProso 2023 and you got there. Okay, let's start in contact. As I said, we take this cantilever, we go to the left side of our force distance interaction diagram. It doesn't matter whether we now take the 612 or the 1.7 potential, as we were really discussing earlier this week. But what is important is actually we are here in this regime, which means we have no cantilever oscillation. The cantilever basically is really deflected, as we see here, with a very strong force, typically 10 nanonewtons or even more. And we call the C deflection by one of the methods we have been seeing, okay? Beam deflection, whatever you name it. We have a strong repulsive force, but there's also, on top of that, adhesion. And that means we have a tip that is firmly contacted to the surface. In fact, it's really clamping on the surface such a way that we have really a strong interaction, covalent bonding, actually. So we can take some test samples like shown here, some kind of, let's say, sodium chloride, or let's say other sorts. We can take graphite, we can graphene, MX2, in order to test what we are doing. I would like to really spend some time on the lithium fluoride, because that's a steady material, and you can see basically, you can see it here in a mimic. So that theory, you say, okay, we have fluorine ions, we have the lithium ions, and in fact we have a big one, which is a radius after Pauling, which is a little bit larger, a small one, big one, small one. And you can calculate what is my resolution in contact if I'm grabbing with my tip over that surface. And what you see in theory is basically this here on the left side. That's the theoretical picture, where it means, okay, along one of these lines here, which is a 100 line, we mostly see the fluorines because they're much larger. And in fact, we're in contact. That's actually the experiment that you see. You see, oh, wow, they are really kind of atoms. Now, if you think hard, the question comes up, actually, why do we see these atoms at all? Because my tip, so to say, let's say tip radius 5 nanometer, typically, should not give us this kind of resolution. And this is really described for the contact mode in the Hertz model, where we have, let's say, my tip with a radius r of 5 nanometers. We go onto the surface, we slightly compress into the surface, and hence we have a certain coupled E, Young's modulus, between the tip. The tip can deform, as you nicely see here, but also the surface can deform. So what you do basically is a series junction of E moduli, and then you can calculate what is the effective E. F is the force you apply, 10 nanonewton we said. And if you do so and you go for this Hertz model, you can plug in the numbers and you come up with A, the contact radius as sketched here, which ends up between 2 and 3 nanometer. So no way to make atomic resolution in contact. Why do we see atoms here then? By the way, 2 to 3 nanometers is exactly the size of this picture, which means the integration over all atoms, meaning all interactions, any of these interactions, pairwise, as we discussed last lecture, has to be taken, which means in the end you end up with nothing. You don't see any contrast. So why do we see, anyway, in contact, sometimes at least, resolution, which we can claim atomic? Where does it come from? And for that, we need to really add something which is known as so-called friction. This has been developed mostly in the 50s, 60s, when looking on hard disk. Your hard drive basically has a head that runs on your hard disk, basically for reading. And the closer you can get, the better your resolution is, which means a higher density of storage data bits, okay, magnetic ones. So we have a reading head, so to say, that slides on the surface. And hence, if you go into contact and we're going to zoom in, and that's the same thing if we take our tip, we get, let's say, either commensurate or incommensurate touching. That means, let's take a gold tip, 111. Let's take a gold surface, 111 again, which means a lattice constant match, commensurate. If you take silicon on gold, for instance, this does not match, which means it's an imaginary, it's an irrational number if you just divide the two numbers of the lattice constants with each other. That's incommensurate. You never have a good fitting on a longer range. So many things can happen, as you see. We're going to have a contact, which means every of these atoms can bind or disbind. We can have a rough surface with asperities. We can have any lubricants. In air, we always have lubricants. So your AFM tip sees, even in SNOM, actually a small, let's say, adsorbate layer of, let's say, water. And hence, when we now go and want to scan with that tip on the surface, so we're going to do that. You see, basically, we're scanning on the surface. It simply means we not only have a vertical force, the K constant of my cantilever, but we also have a lateral force because my tip can get stuck on the surface. I just said these bindings, commensurate, can even be covalent, 2-3 electron volts in binding per atom, which means actually we get stuck somewhere. Or in other words, there's a whole bunch of different, let's say, mimics how this surface now can really go together. Which means we have not only vertical interactions, but we have also horizontal frictional forces. Now we can translate this mimic to the cantilever, because as we said already, we have a K constant vertically, right? But the same way we can also say, I can also use this kind of torsional mode. So I can take this cantilever and you see it, and I can tort it actually very heavily in this way, which means we do the same mimic, the same calculation, okay, different coordinates, and we go in to calculate the resonance mode of this one, which is typically on about 9 times to about 10 times higher than the bending mode. So if you take your lock-in and you look at the higher mode, so to say, at 10 times the frequency of omega 0, you will also see that mode being excited. And in fact, that's actually one of the reasons, it's the main reason why we now see atomic resolution. So let's recap. We go into contact with the cantilever, it's going to stick firmly on your surface, and you start scanning laterally. What happens is, naturally, that when you scan, your tip stucks, and you go, that's my hand, I want to scan here, right, on the back side. But the tip stays until it's basically there, and then bang, it snaps over to the next atom. So we get exactly a snap in on the atomic scale. And this is exactly measured here on sodium chloride. You go, this is a static deflection, which is a static friction force. And then you get a dynamic friction force, which goes atom by atom, bam, 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 bam. So you see, always if we get exactly a stick-slip process exactly the same way as we had this snap-in a vertical case to the lateral case. So you need then, naturally, to measure that, which means this torsional mode easily is measured, for instance, with the beam deflection mode, where we not only have, let's say, up-down, let's say, upper half, bottom half, but we have also left-right possibility to measure with my beam deflection. So, and you see nicely, this is a fantastic atomic resolution as plotted here. You see, the beginning, this actually is the static friction, while all the other thing comes from dynamic friction, as we see here on the forward and on the backward scan. Wow. So it's nothing that you say, okay, the resolution is really vertically given. Now, this goes into the phase as well. So now, Dave Tomanek, in the 90s, has developed now this model saying, okay, when we have this vertical force and also this horizontal force, then let's do the same mass as we saw in this kind of famous plot of snap-in, not vertically now, but we do it now laterally. So we have now the force constant, and you see my force constant is now about this size. I take a sloggy lever, cantilever this one here, and take a stiffer one, like Antonio has, actually. And if we do the mass again, we can just translate. You see, this is a force distance plot, which means actually this kind of dashed line is now, that arrow is my K constant for the torsional mode. It's my torsional K constant. And you see nicely that we have this instability jumping from this point exactly to this point, which means in energy we go up, in energy, and then bang, you go down, up, and down. So that's exactly what happens on the atomic scale. We can measure that. HOPG, graphite, is one of the standard materials that has been tested at that time. And if you take different orientations, you rotate the sample, let's say different orientations by up to 60 degrees, and then you rotate back just for imaging, you see different contrasts. And you always believe these are atoms, and they are atoms. But the phase jump that you have from this kind of in-plane spring constant and the out-of-plane is completely different. So it really matters how you put in your sample. That's basically the take-home message. And second take-home message is atomic resolution is never achieved in contact vertically, but always horizontally. Now let's continue. We want to go more actually into now really contact modes. And most of your samples, like for instance, if you go for gallium nitride or gallium arsenide and so on, they might be polar materials, because they're two different materials. Sodium chloride is polar as well, and so on, which means in the end, we get surfaces or materials which have dipoles in it. And I would like to really develop that now, because piezo response force microscopy is one of these modes in contact who can really differentiate between that. So let's imagine we take our cantilever tip now and we apply a voltage, which is an AC voltage to the tip. If I have an AC voltage, I have a sample, which is shown here. And let's say my charges or my charge distribution can be made by any kind of, let's say, higher or lower order dipoles, P being the dielectric polarization. So if you have a field applied by this AC voltage, and you have this dipole in the field, what it tries to do is naturally a so-called inverse piezoelectric effect. We apply a voltage, it gets longer or shorter, right? So that means it contracts. If this is opposite in sign, it elongates if it's larger. We can do that also for an in-plane. If the polarization is in-plane, and you have a field that goes vertical, what does the dipole do? Well, it tries to orient out of this kind of in-plane orientation. It wants to align with your external electric field. If you have a third direction, which is basically forward, so not in-plane here, but forward towards you, it's exactly the same thing. The tip wants also to orient up. So let's do some exercise. Maybe you can help me by standing up. And we want to do some exercise in order to mimic all these 1 and 2D and 3D modes. So if you go now for the 1D mode, basically, we're just like this. So we adjust the dipole P like this. And if you go now one dimension, we just go down, okay? And we go up, and we go down, and we go up. Okay, so that's really one dimension, as you see, Z direction. Now we want to go for a 2D system, which means you have to also go left and right, okay? So that means basically this is actually what the in-plane mode is doing, the 2D. So if you combine the 1D and the 2D, which means you go up and down, and you can also do it. Okay? Okay? Now let's go 3D, which means you go from forward, backward, okay? Okay? So that means basically we have even the 3D, so we can do all three modes together. We can go down. Okay? Okay, thank you very much. Now, hopefully, you feel a bit better. So we see actually that, yes, we can now do physics with that, not only exercising, but we can also do physics, which means if I take a sample, this is triglycine sulfate, which means it has a flat surface topography. These are atomic steps, as you can nicely see in the topography image. At the same time, you apply this AC voltage, which means you couple to the dipole, which is below the surface. You see nicely that this picture has nothing to do with that one. It's completely different, opposite information. It's just a distribution of bound charges at the surface, close to the surface, coupling to that one. And you see nicely it's a bifurcation, it's only up and down distribution, which means you can plot that in this page. You can increase the complexity. You say, I take barium titanate, which has now an in-plane and an out-of-plane. And if you do so, basically, you see here the in-plane component, IP for in-plane. You see out-of-plane for the other one, which is black-white. Whenever you get a gray here, it means there's no sensitivity to the out-of-plane, which means that's exactly the in-plane component. That's exactly where we have an in-plane or an out-of-plane, so you can distribute that. And increasing complexity means we can also take now a so-called polycrystalline barium titanate. You see different grains, and as you guys know from X-ray, they might be oriented completely differently in real space. But you do this mimic using px, py, pz, and in the end, by analyzing on the local scale, you see nicely, aha, I can compose these three vectors to one vector, which is a vector field, and I know exactly, crystallographically, how my grain stands. So I don't need to really cut it down. I can do that down to the 5 nanometer length scale, and that's very, very important. Next mode, I said we go in contact with our cantilever, we might have charge transfer. Now, we would like to really know how much of that charge is, which means we would like to hook it up in a way that we measure this conductivity by having an ammeter here. So that means, I've just borrowed this kind of sketch here for 2D materials. In any contact, there will always be a current flowing. Remember what I said last two days back is that your tip and your sample surface mostly have a contact potential difference. We will come to that later, talking about Kelvin, which means in the end, there's a driving force. We don't even need this kind of potential as a driving force to apply, because these two surfaces, being two different materials mostly, two different crystallographic orientations, have a difference that drives electrons from the one side to the other. You can do the math and see, and basically see whether this is really going the right way by looking on the current that is flowing. So what you should do is actually, at the same time when you do the tapping, monitor that current with your, so to say, ammeter here, and you can also make a plot out of this. Well, one of my students, Ekta, she was now trying to test different cantilevers, because the question came always up, which one is the good cantilever, and with which one can we do also SNOM imaging? And in fact, the good news is we did SNOM with all these measurements, which are Rocky Mount tip, with the nanosensors, with the budget sensors. They're different in price, as you see, because the diamond coating is the most expensive one, and it has also, let's say, a very small spring constant, but a much larger tip radius. We discussed yesterday, Rainer did that, actually tip radii might be good if they're larger, depending on what you want to see. Here, if you go for conductivity, it's just a big bunch of contact actually on your surface. It's conductive, it's a diamond. That means simply that you have really good contacts. So what you did is now the following, saying, okay, let's go and ramp up and ramp down the voltage. I'm just going touchdown with my cantilever to see, is this still ohmic or is there any kind of injection barriers? And we find no differences for all these cantilevers what is concerning the injection, which means you get a certain capacitance, that's quite clear, but you get also very nice currents. The current offset comes apparatus-wise, that's in the instrument, which has been done here in the park. If you want to have some knowledge on that, that's actually some research we do exactly with this kind of mimic. Is now we're looking, for instance, on so-called domain walls. We rather had actually the barium titanate before, and if you take basically the section which is in between such two polarizations, it's called a domain wall. Now, funny enough, this can be a two-dimensional electron gas. And in fact, actually, your scanning force microscope operated in the conductive mode can measure that. And you can measure currents with this kind of mimic up to a couple of microamps, even milliamps, per domain wall. Why is this important? Because now our current can be analyzed towards its, so to say, topology. It's not only that this arrow goes up, down, but it can turn, it can spiral, which means you got to go for Bloch and nail walls. And in the end, what you get out of these domain walls is a mimic where we have even Hall transport in it. So this is something for the modern research into this. We can discuss later on that if you want. Now, CAFM is very much related also to what we see here, which is the so-called spreading resistance. And this is mostly something not that the physicists are doing, but mostly the semiconductor industry has developed that, saying, okay, we want to know, for instance, as shown here, we want to know defects in our wafers. So it has been developed by taking exactly the CAFM mimic from before, but not looking on the current, but rather on the resistivity. So it's quasi an adaptation of CAFM, looking at the resistivity, and you see nicely that your current then actually, depending on where the current path is going up or down. Be careful on that. What you need for that, in order to really measure good, is you need a very good calibration standard, and this is actually the reference calibration, where semiconductor industry is doing the following. They say, okay, we're going to make some different dopant levels. I'm sorry for the bad quality here, but actually what this shows is, and you can see the mimic here, which is the cut, that you get different P-level dopants, starting from 10 to 10, 11, 12, 13, 14, 15, up to 19. Once you have that standard, you can calibrate the resistivity and hence say something more quantitative on that. That's all I want to say about this mode, and we now go more into non-contact. So we'll leave the contact mode here on the left side. We go again back to the really more attractive mode, and as a take-home message, as I said in the last lecture, is very important. We need to really know, how do we measure that? We said it's a 1,7 potential, which means that kind of van der Waals attraction is very, very weak. It's not as strong as possibly plotted here, and that's why we need a mimic, like for instance oscillating my cantilever dynamically in order to measure that really much more accurate. So we are vibrating the cantilever at its resonance frequency, omega 0, and by vibrating I'm no longer sensitive to the force, but rather to the force derivative, because we're changing that and we're integrating over that one, which means we have now a couple of things to look at. We can look on the phase. That's actually what everybody does so far. But we can also look on the amplitude that really gets smaller once we get closer. Or we can also look actually on the frequency, please.
If you can comment more on two aspects. One is how to get atomic resolution, because that environment counts, right? Usually, often you have to go through liquid, right? That is something that eventually people wants to do that. And the other is that for lithium niobate that easily charge on the surface, with a neoscope, do you have enough parameter to approach and scan on that?
Okay.
In general, what are the parameters that you need to actually adjust for that?
Okay, thanks for the questions. So let me answer the first question first, which is, let's say, what is the environment doing? Well, if you go now here, basically, you set up the mimic right here. We have a humidity which is high. In fact, every surface, when you just take it like this, has at least a mono or bilayer of water on it. So the environment rather acts like a lubricant. So that means simply, if you have this kind of, let's say, environmental impact, we can say, okay, let's avoid that. Let's go to vacuum. What happens then? In vacuum, you have no adhesion layers, which means, let's say, no lubricant there. And the adhesive forces, this one here, is so strong that automatically your snapping will be even earlier, which means you have a strong covalent attractive force. You automatically go into this. The point is the same, that you cannot really go for atomic resolution because the force is so strong here, pulling down your tip, that it's going to be stuck until you really tore your cantilever and then snap to the next position, okay? So the lubricant in that sense helps in order a little bit to weaken up that system. It's not pulled down so much. But on the same time, it's a lubricant, which means it's also mediating the force interaction. So if you take, let's say, an interaction, which is, let's say, a repulsive force, and you go and just scale that by epsilon. Let's imagine for the moment that epsilon, we take non-polar material as a liquid, just like an alkane, for instance. So what it happens is actually you're scaling your force interaction by exactly that epsilon. Epsilon R1 for air, and epsilon effective medium theory for exactly that kind of alkane, which means you're reducing. So biologists do the following. They go into water because the van der Waals interaction is by a factor of 80 smaller, which means you get dissociation, in fact. Or in other words, you can also avoid this kind of strong adhesion. So you can work it out, depending also, similar like the Lifshitz model, actually on the epsilon. Okay, Hopefully that does it. Listen maybe, that was the second question. A polar material has a strong, let's say, surface charge. Now, again, in ambient like we are, you get compensation of that. So similar to really bilayers that are really eating up that surface charge, we get, so to say, compensation, either from external on my surface or from internal. Lithium niobate is now one where you get an external compensation because there are not too many actually internal charges there. Now, if you go for vacuum, this is a huge potential, and one of the ways is to use Kelvin then actually to really balance this off. So you go for electrostatic compensation on your cantilever here, we will see that, and then you have fantastic chances to go for atomic resolution. Okay, let me continue here. So we want to really measure these different materials, and I would like to break the ice again that the frequency is a much better solution to do, because if you go for a frequency shift here, then you can still control the amplitude separately on it, if the machine allows it. And on the other side, you can also see that the different phase informations for optics, for electronics, and so on are really there. So let me go for the first thing, to go for very true atomic resolution. And this was back actually in 1997, some 25 years, where Japanese guys were really looking on indium phosphide. And you see basically this is an atomic resolved surface where we have really defects. So they prepared in ultra-high vacuum, this is room temperature, this surface, said, okay, we take this cantilever, we're oscillating, we're going closer, we know we have no adsorbents, this is a very clean surface. And in fact, they could see exactly this kind of rows with the unit cells matching fantastically, A, to theory, and B, also to former STM images that have been recorded. For those who don't know STM, we're going to really look on the tunneling current, and if you do that basically with a positive or a negative bias, you want tunneling into the indium, which is positively charged, and once on the phosphorus, which is negatively charged. So you can do this kind of salami or whatever you call it. Now, what they found actually, and that's now really an important take-home message, is by approaching this tip, and Rainer was trying to convince you, we need to always do these kind of approach curves. By doing so, what they found is actually that their approach curve is really containing two contributions, 1 and 2. It's not only that you say, I'm going close, I get atomic resolution due to covalent forces. My tip, as you remember, is very, very stupid. It collects any force you want it to really collect. And in fact, here you see the two approaches. One is the short-range forces, which are the covalent ones shown for this image. But if you go for a larger distance, 30 nanometers here, so about this size, you already start feeling electrostatics, which means both Coulomb interaction as well as charges. This is a charged surface as well. It's indium phosphide. It's really a 3,5. So, which means we have to respect what we see here, that whenever we go and do some tapping, I start electrostatically, I come into a regime where I see covalent forces, and then I go in repulsive force regime where I see basically all these kind of effects that I was showing before in imaging, and then I go backwards through the whole thing. And everything is in one phase, okay? We always take one phase out of that. So this is important, that to recap this kind of model where we have now different forces, electrostatic ones, which are longer range, as we just saw, and then the chemical shorter range forces, and somewhere in between, okay, we put our dipole, yeah? So Sasha would say, okay, we go for 300 nanometers somewhere. So from that point of view, it's not so easy. Well, what is the way out? The most dominant one is actually these kind of electrostatics, and that's actually what I want to really break the ice for the next actually couple of minutes, which is how can we compensate for electrostatics? And this is actually going back to exactly this Kelvin probe force mode, which is implemented now into also the SNOM. This goes back, as you see, to William Thomson, or better known as Lord Kelvin. I think everybody knows Mr. Thomson under his really surname called Kelvin. And he developed actually an idea, a mimic. I'm sorry, okay, there's some couple of things missing here. I can easily show what he did. Actually, he took a sample. He took actually kind of a lever, in fact, a vibrating electrode, like this one here, without a tip, and basically put this on top of actually certain materials. He took metal, he took frogs, whatever you want, and hence basically really mimicking and measuring the potential difference that is there. So by having an AC and a DC voltage, he could measure the induced current, the AC current. So take this as a mimic, and now this entangle what we can do with this. And these are the two mimics on the right side. Imagine that we take two surfaces, this one and my hand, and we put them on the same potential. In physics, we say we go to align the Fermi levels, right? So we have basically no potential difference between the Fermi levels here, left and right. They're on the same horizontal line. Since having two different materials means that the work function phi1, phi2 for these two materials must be different, and hence we get a potential that looks exactly this way. Which means we have net a driving force because there's a net difference between these two work functions, and hence there's a current that is non-zero. Let's avoid that current, which means we're going to balance up one of these, okay? So we're going to apply a DC voltage, as you see here, which is exactly the difference between the two, which means my Fermi levels are now no longer on the same level, which means we get netto, so to say, a waterfall to the left side, you could say, which means in the end we have no current, but nevertheless we have a potential difference. So if you want to work now actually with this guy here, we put the tip on it, and we want to really go and really measure that. We want to have it quantitative. Let's see actually whether we can do that, and we're not going too close. And in fact, I want to convince you, yes, you can really measure this kind of work function. You can measure the charges that are really relevant for that. You can measure the contact potential difference and even more capacitance. So this is basically what we have. We have the cantilever. We are vibrating this cantilever at a certain frequency f0. That's my oscillation frequency. And for the moment being, it's not the atomic force that is relevant, but it's really this kind of electrostatic force. Now, electrostatic forces, as you guys know, are Coulomb forces. And if I have a charge on my tip, it's inducing a negative charge on my sample. If I have a negative charge on my tip, it's a positive charge on the sample. It's an attractive force. Coulomb is attractive, and that's why it goes squared. You see, there's a square there, which means we get a maximum somewhere and a minimum. So let's have a look how this looks like. It's like this. We get a maximum here, which means this is the minimal electrostatic force. And anywhere, when we go to the right or to the left side, we're having an increase in this kind of electrostatic. We don't want to have that because we want to measure solely either the local, let's say, optical interaction forces or the mechanical, let's say, topographic interaction. So we need to compensate for that. And one of these methods is to apply a bias voltage to measure this kind of quadratic curvature. The way we do that is actually on top of the DC that we apply to the cantilever, we just put on a small AC voltage, which means a modulation amplitude and the modulation frequency, basically 2 kilohertz, for instance, or you can also go for the second order sideband if you want to. But nevertheless, it's the same mimic. We apply a certain voltage, which means that I'm going to modulate my electrostatic force because my effective U now has different contributions. So this means we want now to measure this, and if I'm developing this mathematically, let's see first of all what the effect of that modulation is. Let's take exactly the DUDC that contains the DC voltage, which is exactly my center here, and some certain modulation. Let's go to the left side of my parabola. This is my Coulomb parabola. And if I'm modulating, you see nicely, let's say we start on the left side, face down, and we go up, down, up, down. So we go up, down, up, down. That's my time trace here on the right side. Very important that you see that this phase starts really low on the left side. If I go on the left side, on the right side with my DC, I'm just changing the DC voltage through my parabola. I'm starting from left to right on a phase shift, which is pi. I go up, or I go down, up, right? And if I go to the middle, where I want to go, which means I'm going to balance off, I go up, down, up, down, up, down, up, down. I see I even increasing the frequency twice. So I go to a second harmonic frequency. So we need to set up a mimic in order to pull that Coulomb force up to here to this point. This is the goal. Now you see also, if you take a large modulation voltage, let's say down here, you're not so accurately really finding your apex of your parabola. The smaller U mod is, the better you can really actually approach this kind of apex of your parabola. And that's a goal why you should not apply to high voltages. There are other goals, I will show you. So let's do the math for that. We're going to have the electrostatic force, and we now plug in everything that we had, the DC voltage and the modulation, which means it's split up in 3 terms. A DC term, so to say, where there's no modulation with my modulation frequency. We get a first order, let's say, demodulation at exactly F mod, and we get a second term at twice F mod. So we go again for sidebands, which means we are having here again the possibility to disentangle all that. Now, which is the most sensitive method? We want to see different comparisons to measure this or to balance off this electrostatics. Well, let's see again. We take the F modulation, that's now basically in frequency domain that we go here. We have about 2 kilohertz, as I said. I have my cantilever here with a resonance frequency, let's say 150 kilohertz. Historically, everybody has really doing this the following way, that you say, okay, I'm going to take this peak at 2 kilohertz, this is 0 here, and I'm going to demodulate it, which means I'm demodulating my force. Now, the force is strong whenever my tip is blunt. So large tips, like 150 nanometers, are good for operating in this kind of AM mode. But you don't get any resolution. But at the same time, you're applying F mod with F0, you get also the sidebands, as you see. You get F0 minus F mod, you get F0 plus F mod. This is simply frequency mixing. And if you're now going, and we call this frequency mode, or frequency demodulation, you can really take that peak out. And since this is now the force gradient, let me go back. It's not the force, but we take the gradient out of this, dF over dZ. We are dynamically modulating. You get the second derivative of your capacitance here too. Which means this signal is not longer sensitive to the force, but force derivative, and hence to the second order derivative. Why is that important? You will see in a second. We take a cantilever, and you have a capacitance, and we're going to make a derivative of this capacitance. Well, the first order is basically that we have a cantilever, and everything is contributing. If I take this derivative, this means the strongest curvature is contributing only, right? And the strongest curvature is my tip, which means I can balance off everything which is background. So for free, not doing anything. I don't need to manufacture. I don't need a FIB for that. I just need to make the right measurements. And hence, we can really measure fantastically. I want to convince you on that. The second benefit is, by shifting to this kind of sidebands, we are right off of this 1 over F noise, which is actually the AM mode that we see here. So Brad Morse, 2010, did some work together with us, actually saying, okay, let's go for a biological sample. We take a membrane, and this was really a serious medical question, because we have cholesterol molecules that are really incorporated into your double-layer cell membrane. And the question was, why is somebody actually cholesterol sick or so? Or can we really measure that somehow? And the answer was yes, we can, by comparing, for instance, different such modes by using electrostatics. Lift mode means you're measuring, first of all, in contact, then you go away 30 nanometers, and you measure simply what is there. In AM mode, it's exactly what I showed in my frequency diagram. You go to the left, 2 kilohertz signal, and demodulate that one. And on the right side, the FM is exactly, you go for F0 plus or minus F mod. And you see nicely from the resolution that you see, and also from the quantitative values, 400 millivolts differences, that you can nicely see actually these kind of surfactants, which are the cholesterol ones shown here in a mimic. The black ones are the ones. These are the bad guys, the cholesterol in the cell membrane. So this is actually breaking the ice for really high resolutions. And I would like to also show you the other point. I said the modulation voltage needs to be very small for that, not only because of resolution, but look here, we have now a modulation voltage of 550 and 5 millivolts, which means in the end, you don't want to excite a band transition. Imagine you do that on a material like, for instance, molten disulfide, or you go for silicon, and you have transitions, meaning gaps of 0.7 volts or so, and if you apply a voltage of 500 millivolts, twice that is 1 electron volt. You easily induce additional transitions of your electrons. You don't want to have that. You want to measure what is there. So, in fact, this FM mode can even go down, as you see, to a 5 millivolt oscillation amplitude and still do a very good job. Okay, let me show now 5 examples that how we can apply, and 2 of them are really also SNOM-based. Let me start simple. We take a molecule, which is actually so-called surface assembly molecules, SAMs, which have a COOH termination, carboxylic acid, which is a polar material, and the other one has a methyl ending. You put them, you stitch them on the surface, they stick there on gold, like as you see here, there's a silicon and gold layer on it, and you just measure. They have quasi the same height. There's a small height difference of 0.01 angstrom. That's what you see here, very small. But what is more important is actually this kind of electrostatic contribution. This is now the surface potential Kelvin system, where you nicely see the COOH and the CH3, which are different. And in fact, if you do the spectroscopy, that means you take exactly these parabola, once on the COOH and once on the other one, which is the methyl terminated. You see the difference from 1.7 to 3.2, 1.4 to 1.5 electron volts difference. Huge. So when you go and not compensating for that, you always think everything is the phase because of topography, which is not. It's all electrostatics. Second example, high resolution. We take a material which is a copper tetrabutylporphyrin, and you see the molecule sketched here. This is just 1 nanometer by 1 nanometer in vacuum. And you see basically there are 4 legs, 1, 2, 3, 4 butyl legs, and we have 1 copper atom in the center. And we do the same mimic, exactly the same machine, but we go basically for high resolution. This is topography, you don't see too much. And if you look on the Kelvin signal, the surface potential, you see nicely 1, 2, 3, 4 dots, which are exactly these 4 legs, which means you get a resolution which is below even 1 nanometer on that. And the reason for that, again, is exactly this kind of curvature, the derivative of my tip, because we go for the second derivative of my capacitance. That's why. Third example, we come to SNOM. So we did a couple of measurements, actually. Tobias did that and was publishing that also lately to say, okay, why not to look at the near-field signals, second, third, fourth order, with and without applying this kind of Kelvin mode? What is the impact? How much am I doing wrong when I'm not really switching it on? And you see basically that's the point on the top, and the Kelvin is off. You see there's a 0 volt, which is the lowest curve here, and then we go up to 4 volts. We normalize this to 1. And you see nicely how the contrast is changing. Typically, the 25% with respect to the 100% difference is there. And if you go and say, let's go for a separate feedback loop on this F0 minus F mod now, switch the Kelvin on, you see all these curves, independent of what you apply, are all the same, which means you can be sure that if you plot this signal, the phase signal that you still have for your SNOM is exactly the optical phase that you want. So that's a good message. We adapted that also together with Thomas Taubner's group. So Julian Barne was really actually doing some measurements with us on a so-called phase change memory material, which is exactly this one. It's a chalcogenide. And then saying, okay, for the phase change, for just with an application, we want to really go. We start with an amorphous system. We're going to crystallize it, or we're going to reamorph and recrystallize it, so you go forward, back, and thermally. Okay, you can really do this process in a repetitive way. What happens then in the end is actually you get areas which are reamorphized, and you get areas which are recrystallized, and so on. So in the end, you have 4 different variants. And the question is, how can we see that? The primary idea was to go for SNOM only, that's the reddish curve as you see, and see it by SNOM. And the answer was, no, we need to do much more on that. We need also combine it with the Kelvin. So we have now really hooked up our F3 electron laser up to 60 microns, as you see here, because to hit really the sample resonances, that was the goal. But on top of that, also applying the Kelvin signal, and that's the bluish curve. So now we can go step by step through that and see, if I would really interpret only the red curve here, I would miss a couple of phases which we have in these pictures here. For instance, this recrystalline or the reamorphized surface form, which shows only up in a Kelvin but not in an optical signal. You don't see that optically, but you see that electrostatically something is happening because the atoms reorient in this kind of chalcogenide system. I don't want to go too more into detail. You can see that also in Julian's work, which is published here. But it's important that you combine these modes. Last example, number 5, quantum capacitance. And I do know that many people in here are also working into the field of 2D materials, right? Take a graphene layer. Let's imagine this is graphene. And we guys know, okay, we want to really put it on a surface. Now, if you look on this graphene layer, question to you, do you expect that the charge on this side, freestanding graphene, is the same like on this side? What do you think? So take your Kelvin, for instance. You would say, okay, I'm approaching from this side, and I'm approaching from this side on my graphene. Would you think it's the same? The answer is no. because we get, in fact, even on this kind of very tiny, tiny monolayer system, a difference, similar because actually on the atomic level, because the charges in a p orbital, for instance, can only be on one side. So that means we get actually a charge imbalance between the two sides, which is causing exactly this kind of quantum capacitance. Now, if you take two layers of graphene, they're compensating. So one way, and that was exactly our thinking really back in 2013, okay, is why not to take the second sideband, as you see. We have here the first sideband, but we're now taking the second sideband, because you could see actually in our formula, in our second sideband, there's nothing actually now concerning this kind of really surface potential difference in here, but only the U mod and twice F mod, and we can measure the dc over dz directly. So that means by using this kind of sideband mimic, we can also have a picture of that. And that's exactly what we did. We took actually graphene on silicon, optical image lets us really differentiate 1, 2, 3 layers in there. In the topography, it looks like this. In the Kelvin, it looks like this, that we see a potential difference of 150 millielectron volts between the first and the third layer. And then we took actually the quantum capacitance between the first layer, blue, just a monolayer, and a bilayer. For that, we were applying on the bottom a gate voltage. You see, this is a gate tuned between plus and minus 15 volts in order to inject more charges. So this is exactly the calculated charge density, minus and positive, so to say, that we have there. And in fact, you see nicely how this quantum capacitance is exactly at a bias of about 5 volt changing. So this is another way how you can differentiate between mono and bilayers by using exactly your mimic who is already there and really looking on that. Okay, with this, we're coming to a second very important thing. Imagine your sample now has a magnetic moment built in. And this is exactly what is shown here. We now take a sample which has a magnetic information. These dipoles so far were electric. Now let's get them different orders. Let's get them also magnetic or magnetoelectric. Now the question is, how can we disentangle that? Because that goes also into our phase. And the only way we can really go for that, it's not as easy as with electrics, because here we can apply voltages to the cantilever, is that we do a so-called two-pass approach, which means we go into contact, we scan in contact, or let's say in tapping, and then we pull back the tip about 30 to 40 nanometers and follow up this contour directly, which means now we have only the long-range forces. So everything that is shorter range, between 30 and 40 nanometer, which is exactly the covalent bondings, which is also electrostatics, is gone, and the only thing that is remaining is my magnetic interaction. So we did that, and we have a lot of mimic on that. I don't want to bore you on that, but what is important is now that you can really use that for modern materials, so-called skyrmions. So this is actually going back really imagine sitting in your jacuzzi, actually, and the water spilling around you, right? Either left, right, or right. So these are really now magnetic spins that you have, and they're really forming different orientations. For the specialists, these are Bloch and Neil and anti-skyrmions. And in fact, your mimic with the tip at the same time is doing this kind of MFM imaging. I would like to spend one word on that, because maybe that's interesting that you see, okay, that the difference between these kind of arrows, equally as I said before for electrics, can turn in different ways. Imagine, how do we go from this arrow to that arrow? In fact, there can be many ways. We could have a hard easing wall, which means I go up to the wall like this, and then I'm just flipping within 1 unit cell or so. But there are other ways how you can flip that, which means you can have, let's say, along your K vector, a rotation of that vector. You see, basically, it's called the Bloch wall. So your arrow basically turns like this, like it's turning, okay? It's a Bloch, so to say, transition. Or it can also turn as a nail wall, which means you're not leaving the plane, but you're turning exactly in the same plane. Now the question is, how sensitive am I to this, and is this affecting my phase? Because we come back to the famous phase that we want to measure. And the answer is yes, it is. Here we have a sample where we were able to prepare on nickel both walls. The zigzag walls are so-called Bloch walls, and the straight walls that you can see here are so-called Néel walls. So you take your tip and you say, okay, I'm scanning along this here, or I'm scanning over that zigzag wall, I'm scanning over that straight wall, in simply looking actually, what is my phase that I'm really measuring at the end of my microscope doing? And you see nicely my phase, here it just goes up like a Gaussian curve, and here basically it goes like a sine curve. It goes up and down, which is point symmetric, and this one is again mirror symmetric. So if we come back to this cosine sine stuff, you remember basically conservative, non-conservative forces from the last lecture, and the same happens here. Now the phases, as you see, this is a phase signal, is the one you measure. And imagine you have something like a magnetic ion on your surface or some kind of magnetic inclusions on your 2D material. This is exactly what happens. It's giving you a contrast in your phase of this kind. And you interpret it as an optical signature. So be aware of that. Good. So now, we've done a lot of these things, and I would like to finish, if I don't know, Mrs. Chairman, I have 2 minutes, or 3 minutes, or 5 minutes? 3.5, okay. Okay, good. Maybe I'm not going to make it completely, but nevertheless, you can ask me later, and you get also the slides, into time resolution. Let's go for time resolution with these kind of blunty scanning force microscope tips. And I would like to start with something which I call pump probe Kelvin, which means we want to go not only to measure DC, what is the potential there, but we want to see time dynamic, how that changes. For instance, you're operating your organic field effect transistor, or you want to see charge transfer between molybdenum disulfide and tungsten diselenide, and so on. And exactly we have been setting up such kind of a possibility to say, well, my tip and my sample can do much better things rather than actually only applying DC or AC voltages. And the idea was actually born to say, okay, instead of actually using this kind of sine wave only for demodulating, remember we apply an F0 voltage to my cantilever in Kelvin in order to make this sideband. Now let's make this kind of a little bit more complex. Let's take that sine as an envelope and then actually put a pulse generator into it. So you see again, the envelope is exactly the sine envelope, but we're going to really shoot with a pulse generator in very high frequencies. In fact, it's going up to a couple of 100 megahertz in there. So basically what you're doing actually is an amplitude modulation of this signal here. The envelope is still there. It can still regulate. But what you're interested in is exactly these pulses. Why? Have a look here. Bang. Okay. So again, on the top, we see this kind of envelope. And this is, so to say, my very fast pump, so to say, signal. Imagine we have a sample. We are the sample here in this audience. And we are applying, that's exactly what you do always, you just contact your sample, and you want to apply a voltage or a charge to your sample. So let's imagine we are going to apply these pulses to your samples. What does it mean? Okay, the contact is on this side. We're injecting charges, let's say from this side, with a repetition rate of, let's say, 100 megahertz, which means the charges, they move, and maybe they are eaten up somewhere because of potential drops, passive dissipation, and so on. So they don't make it possible to the other end. At the same time, we're applying the same pulse voltage to the tip. So that means what I can do is actually kind of an electrical pump probe, which means I'm getting my charges in from the right, I'm standing here, and I'm going to basically make a coincidence experiment saying, hey, charges, are you already here when I'm doing my pulse on my tip? If they are there, fine, I get a 1. If they're already gone, or if I'm too early, delay line, then I get a 0 signal out. So the whole thing goes as good as your pulse width is. If the smaller that is, the more delta function you have, the better resolution, because we come back to exactly, I don't know who said that, but if you go for a convolution in frequency space, if you get a pulse and you convolute that with a delta, you get the pulse out at the position where you are and the time where you are. So you get a very high time resolution. Everything is about Fourier transformation. Yeah? So let's see whether this works. So we have 2 experiments that you can do. You can say, well, I can stand fix with my tip here. Just let the pulses in, and I'm going to make a different delay line, which I get a time trace. Or I say I'm fixing the delay, and I'm going to scan. Okay? And then basically I see the wave fronts where my electrons drop. And that's what we did on an organic field effect transistor, OFET, made out of 30 nanometer pentazine with 2 electrodes. These are quasi-finger electrodes. You see these electrodes in the top left and here on the right. So this is exactly this topper edge. The film doesn't look so nice, crystalline. You see there are many, many different crystals in it. But now let's do the experiment. We pump the system, and let's say the delay is 0. No delay line between injection and measurement, which means, okay, they must come, and if I'm going to scan right here, okay, I'm not expecting too many of these electrons reaching my other bitter end, actually. And you see nicely, one of the wavefronts here, typically monitored here for about 1, it's basically it's stuck here. And it's not a straight line of an equipotential line, but it's meandering, simply because we have a structured sample. So all these kind of grains have a little bit different surface potentials, and that's why actually the potential walls that we have here, which are reflecting the charge density, are that kind of meander. Let's increase the time. You're going to make like stroboscopic images, bang, 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 and you see 8 microns, 10 microns, the whole wave is gone. So we can see the wavefront of electrons for a certain potential moving along that surface. And in fact, the physics behind that is now that you plot the x-axis and the y-axis. The x-axis is the time, the y-axis is space. And you, as you learned in physics, first course is actually if you have something like space and you have time, what you get basically with the slope is the velocity. So it's as simple as this. You see directly how these electrons move in the system by using this kind of pump probe stuff. You see even more, sorry, that was wrong. You see even more, because if you turn on, so to say, your gate, you say, okay, electrons, you can go in, and then you say, I'm going to shut down. Electrons, stop. No more electrons from here. Okay, barrier. And you see basically these electrons that are in there in a channel for from about 10 to about 16, for 6 microseconds. They say, okay, we feel really happy in the pool. We don't want to get out. Okay, it's just opposite. They can't get out. They're stuck in it, and that actually means your device is dead for about 6 microseconds. So you're very slow on that. So what it means in the end is you should improve to get the electrons out, and you know how much by taking quantitative data, how much that is, how big the barrier is, time resolved. Okay, last slide is we did the same thing actually with optics now. Say, okay, we go for pump probe now in our really terahertz near field, which means we take now 900 gigahertz pulses, and we go for doing similar things. And in the end, what we got as a very nice result is that the lifetime of our phonons in this kind of really topological insulator material really very much depends actually on this kind of how you pump and when you measure. So you can take a similar mimic for any of these kind of scanning probes. Bottom line message, it's not limited to the time resolution of your scanner. It's not limited to the resonance frequency of your scanner. You can do much better on that. And the holy grail is always Sideband. Okay, with this, let me summarize. We have basically different signals, and we are too much stuck at the moment to the phase, possibly. You should really work on that. We cannot get atomic resolution. We need the friction for that. And yeah, you can read it. Thank you very much.
Thank you very much, Lukas, for a very entertaining lecture and also some gymnastics. So now the questions, okay?
Thank you. It's very wonderful. Again, everyone can see it's a very different level you are. Like I always believe that
I'm a little bit higher. That's right.
Yeah, it's. I believe that in near specs the AFM is quite advanced, but I see there is a lot of room for improvement there.
Exactly. There's a lot of room at the bottom, like Richard Feynman said.
But my question is regarding like mainly the first half, or basically all the images where you can see this nice atomic or close to atomic resolution scale bar, just few nanometers. It's amazing. The question is, well, what is the environment is required for that, and what kind of tip would you recommend to use, like sharp, not sharp, metallized or not? And a little bit related question is, how about the water? There is a myth that there is always like a layer of water.
Yes.
Is it such, and do you need to do that, something with it or not?
Okay, many questions, short answers.
Sorry.
So the water is there. In ambient, we cannot do much about it. What happens is actually when you dip into it and you do that in contact, is actually you're pulling up capillary forces, which means it's really always there. It's pulling back and pulling down actually your tip onto the surface, faking a more, let's say, attractive force than there is with van der Waals. It doesn't mean that you cannot get atomic resolution. In fact, tapping is exactly good for doing so. The point is not that you're not getting the atomic resolution. The point is that you have to be aware of the quantitative interpretation of that, because your data, so to say, are convoluted by many other effects. So the lateral spacing, if you say, well, that's actually what I'm up, I can really do that. Do you find a way to compensate even tapping in water, or is good? Tip-wise, naturally, is that you need a tip that is sharp enough for getting atomic resolution, and you need, so to say, compensate for the other forces that could mimic at the same length scale. Okay, so the electrostatic should be off. So I'm recommending to do really Kelvin routinely on all machines. Let that run, even if you don't record it, but if you record it, you even get some more papers out.
What about sharp enough? How sharp is
okay.
it?
Now, fact is, so to say, sharpness, as you see, basically in scanning force microscopy, it's not that we get an exponential dependence like an STM. No? And if you go for a 1.5 or 1.7 potential, the first atom and the second atom in your tip, so to say, only have a factor of 2 to 3 difference in force interaction, which means it's not that much, right? Which means you have to really go subtly. What I recommend for atomic resolution is really not to take a large amplitude of oscillation, but really small amplitude, as small as you can, and improve your signal-to-noise ratio and your mimic of sensing.
Yeah, thank you very much. It's very clear that combining all these techniques is very beneficial. But what I'm wondering, and I think we discussed this already quite often, also with aspect, does it make sense to combine all that in one instrument, eventually do it simultaneously, or does one enter then into some compromises and some, let's say, is it, and how, what do you think? Is it let's say, interesting to do it all simultaneously, or, and even possible?
So, okay, to do it simultaneously is demanding, and in fact, you need to know what you do. Because basically in the end, I didn't say that, we're running about 6 to 7 different regulators in order to get this information disentangled. So you need to know exactly what's the sideband, what is actually the low-pass filter, what are the RC values. But the point is, so to say, to start, we don't need to kill the bug really with something large. But what I like to say is actually the most effective one is actually electrostatics. And to implement that one as a first shot is very important. Now, the bottom line message is that my cantilever, as said, it measures everything, you know. And the question is at what level? And possibly if you remember that one of the slides in my first lecture was different levels of energy interactions. So if you say, well, I'm going for, let's say, 1 electron volt interaction, which is the major, typically, hand-waving order, then I don't need to care about 1 or 2 milli-electron volts on that level. But nevertheless, physics happens also on that level, you know. So what I would like to break the ice for is that the machine, any machine that you buy, has the potential to really do that. The question is, how sensitive is my mimic on the one side, and do we need that? In SNOM, we can clearly say, well, you should recommend, or you should really compensate for electrostatics, and then actually go for really disentangling that phase. Because already that, as I showed, is giving you much better signal-to-noise ratio and much clearer 2 omega, 3 omega, 4 omega measurements. Yeah.
Okay, I think we have to finish because we are a little bit delayed, but thank you once more for a very excellent lecture.
What I didn't say, there's another gadget here as a mimic, because if you want to do magnetic force microscopy, there's a quasi-handy MFM measurement here that you can also play with later, okay? Thank you.
Okay.